I want to do two more quick examples of using this new notation called the differential, which is the dt we were talking about. And I emphasize it's not a new concept really. We were already using it. We just are now realizing we might want a name for it. So if we have another case of this temperature as a function of dial set, where T is the temperature, X is the dial setting. And let's look at this. And suppose we know that we want, just to kind of change the numbers around, suppose we want the temperature to be 100, and we figured out that with dial setting X equals 2, that we can achieve that on the nose. But it's rather sensitive. We discover that the slope of this tangent line, so the colors come out in the video at all. We discover that the slope of that tangent line, we don't know the formula for this function, but we discover that the slope of the tangent line, in other words, f prime of 2 is equal to, let's say 100 and, well, let's say 200 to make it really simple. Just make it really simple, 200. Okay. And right at the end of class, I was talking about one new notation we have for that is that says the idealized approximate predicted change in the temperature given some small change in the dial setting should be 200. So this is an alternate notation for the derivative, the slope of the tangent line. It says that if this were actually a straight line, and this dt were the actual change in temperature, it says that the rise over run would be exactly 200, no matter what I did to change the temperature, whether dx was tiny, tiny, or big, or medium, or negative, or positive. Now in reality, the life's more complicated than that. The actual change in temperature, especially if I walk really far away, if I make delta x, or I also think of that as the same as dx, really big, then the tangent line ceases to be a really good prediction of how much the function changes. And delta x, which is after all, or delta t, which is what I'm really interested in most of the time, ceases to be the same as dt. But as long as delta x is small, you notice there's not a heck of a lot of difference between that green line and the sort of yellowish curve. And that's the situation I'm mostly interested in. So let me just show you how this way of writing things makes the calculations we were doing really easy. It says dt over dx equals 200. And I'm just going to take that seriously as a fraction. And now let's suppose I need to get within 20 degrees Celsius. I need to be within 120 and 80 of my actual temperature. And I'm going to just use the green line. That's the deal with calculus, is that we're just going to throw away the actual function because it's too complicated. It's the beautiful thing about calculus. You throw away anything that's too complicated and replace everything with straight lines. If this were the green line, then it's just a straight line problem. And this makes even the working of that straight line problem really easy. We just measure this. How much leeway do we have in the temperature? That's dt. That's how much our temperature is allowed to change. And we're using dt instead of delta t because we threw away the old function where the delta t lived. We're in dt land. So we just set dt equals 20 and plug it into here. 20 over dx is 200. Cross multiply. dx is 20 over 200 equals 0.1. That's how far I can go. End of story. So this is a very handy notation for the derivative that says the idealized predicted straight line change in the output divided by the change in the input that you choose is equal to the slope. And then then if you know either dx, you can calculate dt. If you know dt, you can calculate dx. Very easily, it's just a very simple algebra. One place where we're actually very used to doing that is with velocities. So suppose I say I have s versus t, and it's like this, maybe like the scooter in the Porsche problem we had a while ago. And right here, at t equals 30, say, 30, maybe 30 minutes or something like that. Well, let's say hours. So let's not have 30. Let's say t equals 3. After 3 hours of travel, we find that the derivative ds dt is equal to 80 miles per hour. Then what can we do? What kinds of questions can we answer with that? Well, we can't answer any precise question about the motion of this particle using this one number. Anything, if I say, how far did he go in the next 10 minutes? If you want a precise answer, I don't know. How far did he go in the next 2 seconds? If you want a super precise answer, I don't know the answer to that question. The only kinds of questions we can answer with this information are, the only kinds of answers we can give, rather, are approximate answers, basically based on taking this complicated function and pretending that he was going at that velocity for all of time. And we just have to warn people that if you ask me questions that walk really far away from 3, they're likely to be really bad estimates. But if I stay really near 3, they might be pretty good. And that just reduces it to a straight line problem. And this notation just gives handy names to the change in time we might be interested in or the change in position we might be interested in. So a version of that would be, suppose I just wait after 3 hours, suppose I wait another 6 minutes. In other words, 0.1 hours. Then ds is just going to be ds dt times dt, because they cancel. And that's just going to be 80 miles per hour times 0.1 hours is 8 miles. Hopefully that shouldn't shock you that my prediction for where he's going to go in 1/10 of an hour is 8 miles. But it's really an approximate prediction. It doesn't take into account, it says he can't change his velocity basically for that to be perfectly accurate. But this notation of ds dt multiplying by dt to get ds is a very handy way to think about it. So that's one version of it. What about, suppose I see, or I want to know how long it's going to take him to go an additional 4 miles. Then again, ds dt, I'll do it a little bit of a different way, equals 80 miles per hour, and I'm just going to plug in 4 miles. Just like I did the original, the one on the board previously. And I just solve for dt. dt is going to be 4 over 80, 1/20th of an hour, or 3 minutes. It's going to take him 3 minutes, my prediction, to go the 4 miles. Not surprisingly, that's half of the 6 minutes that was going on up here. So it all ends up being very nice. If you have this equation, idealized change in output divided by given change in input equals a fixed number that you know, that's very useful. Where it's going to become more useful, and one reason why the book delays this, is we don't have a lot of ways of getting this number easily yet. But we're going, in the next couple weeks, we're going to get a lot of ways of calculating this number very easily. So we're going to have exactly this situation. We will have calculated this with some very cool techniques using some funky algebra rules that we're going to derive. And then we're going to plug it into an equation like this and be able to predict a lot of things about how much things change, at least approximately.